Hello dear students, welcome back to my lesson. To continue the previous lesson, today also we are going to talk about the Lenz's law and explain in detail about the Lenz's law. The Lenz states that the magnetic field of induced current is opposite the external of the magnetic field. And as you can see in this figure, we have many different cases of the Lenz's law. Look at the first figure. In this figure, we have a bar magnetism, okay, and a circuit. In that case, when we approach the north pole of bar magnetism into the coil, this end also becomes north pole, okay? And according to the right-hand rule, we can find the direction of the current, okay? After finding the direction of the magnetic field by the Lenz's law, we can finding the direction of the current at the resistance. So in this case, what is the direction of the current in the resistance? Look, the direction of the resistance by using right-hand rule, this is the north pole and this is south pole, okay? And the direction of the current is upward above the coil and downward below the coil, and it will be like that. So the direction of the current here is upward and below the circuit is downward. So it means that the direction of the current is from left to right, okay? But in this case, what is the difference between these two cases, okay? We approaches the north pole, okay? When we approaches the north pole, this end also becomes the north pole, okay? The north pole. And this end is south pole. But this case is different from this case. Why? Because of the wrapping of the wire. The wrapping of the wire at the end of the north is located below the iron rod, but here the wrapping of the wire is located above the iron rod. Look, if you put your fingers, the direction of the current is upward, with this case, upward, okay? And here is downward. So it means that the direction of the current is reversed. So in how many ways you can reverse the direction of the current? By reversing or by inversing the direction of the pole of the magnetism, by changing the pole of the magnetism. And also, if the poles of the magnetism does not change, how can you change the direction of the current? By changing the wrapping of the wire or wounding the wire around the iron rod. Another example, the second example, if we approach the south pole, if we approach what? South pole into the circuit or coil, this end becomes what? Becomes the same pole. So what we approach it? South. This end becomes south pole, okay? And this end is south and the other end, it becomes north. If you put your right hand, this is north, you have to close our fingers. The four fingers represent for the direction of the current, and the thumb is the direction of the magnetic field, and it is north, okay? If we close our hands, the right hand, the direction of the current is downward, okay? It means that from right to left. And also by changing the wrapping of the wire without changing the pole of magnetism. In both cases, we approach it the south pole. And in both cases, this end is south and this one is north. But why in this case the current is directed to the left, but in this case the current is directed to the right? Because of the wrapping or wounding the wire around the iron rod. So here, look, the iron rod, the wire is wrapped here at this end, at the end of the south. The wire is located below the iron rod, but here the wire is located above. Look, but here the wire is located below the iron rod. So this is very important for changing the direction or reversing the direction of the current, okay? The Lenz's law the rule for finding the direction of the induced current is called Lenz's law. It means that the Lenz's law provides information to finding the direction of the induced current, not its magnitude. Okay, so by using the Lenz's law, we can finding the direction of the induced current that results through the change of the magnetic flux through the circuit. The Lenz's law states that the magnetic field of induced current, the magnetic field of what? Of induced current. It means that the induced magnetic field is in a direction opposite or opposite to the change that created it. Okay, so according Lenz's law, the induced magnetic field does not opposite the applied field, rather than they opposes the change of the applied magnetic field. Lenz's law can be used to find the direction of the induced current, not its magnitude. Okay, the Lenz's law provides information to find what? Direction, not magnitude. Okay, the Lenz's law is the law of conservation of energy. Why? Because the total magnetic field stay unchanged, stay constant. The magnetic field of the induced current and the magnetic field of the external field totally are constant. Okay, so because the field of the induced current does not oppose the applied field, but rather the change in the applied field. Okay, so if the applied field changes, the induced field tends to keep what? The total field strength is constant. Okay. Question 2 from chapter review. This question. Explain how Lenz's law allows you to determine the direction of an induced current. How can you determine the direction of the induced current according to Lenz's law? So we know that when we approach the north pole of a bar magnet toward the circuit, the end of the circuit becomes the same pole, becomes north pole. If you determine the direction of the magnetic field, so it will be very easy to find the direction of the current according to the right-hand rule. The direction of the induced current is such that its magnetic field will oppose what? The change in the external magnetic field, not magnetic field itself. It is opposes what? The change in external magnetic field. So explain how Lenz's law illustrates the principle of energy conservation. Actually, the Lenz's law illustrates the conservation of energy. Why? Because the total magnetic field does not change. Okay, by opposing change in the external magnetic field and the induced magnetic field prevents what? System's energy from increasing or decreasing. That is why the Lenz's law illustrates the conservation of energy. We have some note here. The direction of the field of induced current does not oppose, as we studied and I told you before this note. Note number 2, Lenz's law does not provide information about the magnitude of the induced current. So who was the first scientist discovered the magnitude of the induced current? The Faraday's law. But Lenz's law, he found the direction of the induced current. Okay, does not provide information about the magnitude of the induced current or induced EMF. But Lenz's law allows you to determine what? The direction of induced current in a circuit by opposing the external field. Okay. To calculate the magnitude of the induced EMF or induced current in the circuit, we have to use what? Faraday's law. So if in the exam they will bring like that, which of the following scientists discovered the magnitude of the induced EMF and the current? Faraday. Which of the following scientists discovered the direction of the induced current? Lenz's law. Okay. We have this question in the figure below. What is the direction of the current in the resistor? What is the direction of the current in the resistors in these two cases? A, if the magnet is moved to the left. If the magnet is moved toward to the left. So we know that if the magnet is moved to the left, it means that the north pole is moved away. North pole move away. When the north pole is moved away from the circuit, this end becomes opposite pole. It becomes south. If this end is south, it means that this end is north. And put your right hand rule by using the right hand rule. This is north and this is south. Okay? Downward. The current is downward. For the first case, if the magnet is moved from left to the left, the direction of the induced current is from left to right. From where? From left to right. For the first case. In the second case, if the magnet is moved to the right, if we approach the north pole of the circuit, this end also becomes what? Becomes north pole, and this end becomes south. Put your fingers by using the right hand rule. This is north and this is south. The direction of the current above the iron core is upward. The direction is what? Is upward. So in the resistance, the direction of the current is from right to left. For the second case, the direction of the current is from right to left. Branch A, from left to right, and branch B from right to left. Question 5 from chapter review. It's a very good question. Okay, be careful. This question says, rapidly inserting the north pole of a bar magnet. But be careful, in this question, they will not give you the figure. So you have to figure by yourself, okay? How can you sketch the figure? Now I'm going to tell you, okay? Rapidly inserting the north pole of a bar magnet. Into what? Into a coil of wire connected to galvanometer. So the galvanometer is a device can be used for measuring very low currents. Okay, so this galvanometer tells us about the presence of the current. Okay, now we have to draw. Look, inserting the north pole of a bar magnet. Draw a bar magnet, north pole and south pole. Into what? Into a circuit. Into what? Into a circuit of coil. Okay. So in that case, this is the wire and connected with what? With galvanometer. So what we have here? We have a galvanometer, okay? And causes the needle of galvanometer deflected to where? To the right. So the galvanometer's needle deflected to where? To the right. So this deflection to the right. So because of the deflection of the needle, we can find the direction of the current. So the direction of the current, it should be to the right. Why? Because the direction of the deflection of the galvanometer has the same direction of the current. When the current directed to the right, the galvanometer also deflected to the right. When the current directed to the left, the galvanometer's needle directed to the left. In this case, the galvanometer is deflected to the right, so that is why the current also to the right. Okay? When the current is to the right, it means that this, by approaching or by inserting the north pole, this end is north and this end is south. Okay? So that is why in this case, the wrapping of the wire should be like that. Otherwise, it will be wrong. Be careful. Okay? In this question, the wrapping of the wire near the south pole should be above the iron rod, and the wire with the north pole should be below the iron rod. So as the question tells us, when we inserting the north pole into the circuit, if we approach the north pole, this end also becomes north. Okay? And put your fingers, the direction of the current is downward in the galvanometer. So the deflection of the galvanometer is deflected to the right. What will happen to the needle if you do the following? We have 3 cases, okay? For the first case, if we pull the magnet out of the coil, if we pull the magnet what? Out of the coil. In that case, look, for this case, this is the magnet, north, south. out of the coil, it means that when we move it away the North Pole, the deflection of the galvanometer will be opposite with the first case. Why? Because we reversed the direction of the current. And look, what happened with the needle? We have to find the direction of the needle of the galvanometer. Look, now we don't know the deflection of the galvanometer is deflected to the right or left or stay at rest. In the case when we move it away the North Pole, this end becomes what? Becomes south. And this end becomes what? This end is south and this end is north. Put your finger, right hand rule. The direction of the current is upward. Is what? Is upward. And here is downward. The direction of the current is to where? To the left. When the direction of the current is to the left, the deflection of the galvanometer also deflected to the left. So in that case, we can find the deflection of the galvanometer. For the first branch A, the needle deflected to where? To the left. Okay? For the second case, let the magnet sit at rest in the coil. When the magnet is sit at rest, it means that there is no relative motion. When there is no relative motion, it means that there is no deflection of the current. Okay, no deflection of current. For branch C, thrust the south end of the magnet into the coil. In that case, for branch C, when we approach the South Pole, this end becomes south and this end is north. By using the right hand rule, the direction of the current is upward. Here is deflected. The needle of the galvanometer is deflected to the left. Deflected to where? To the left. Okay, that is all for today. Inshallah, in the next lesson, we will explain more about the section 1. Thank you for listening.